Hi everyone and welcome. My name is Alireza Golahmar. I'm an industrial PhD student at Technical University of Denmark, Department of Mechanical Engineering. Today I'm here to present my work on phase field modeling of environmentally assisted fatigue at the COMPLAS 2021 conference in Barcelona. We see that there is a growing interest in understanding and optimizing the fatigue behavior of metals in the presence of hydrogen. Two aspects have mainly motivated our study. First, hydrogen-assisted cracking is a well-known concern in many industries. Hydrogen is everywhere and it significantly reduces the ductility, strength, toughness, and fatigue crack growth resistance of metallic materials. In addition, hydrogen is seen as the energy carrier of the future and therefore fostering a notable interest in the design and prognosis of infrastructure for hydrogen transportation and storage. And in the majority of these applications, what we see is that susceptible components are exposed to alternating mechanical loads, and therefore being able to predict the synergistic effects of hydrogen and fatigue damage is of utmost importance. Okay, let's get started with the theoretical part. As you might already know, the phase field fracture model has recently emerged as a promising variational approach to capture initiation and propagation of complex cracking patterns. The idea behind this method is to use an auxiliary field to track the crack-solid interface implicitly, so to say, in the sense that we no longer have a sharp interface, but the auxiliary variable, the so-called phase field, is telling us where the interface lies. For example, the phase field can take the value of 1 in the crack phase and the value of 0 in the undamaged material points and varying smoothly in between. One of the beauties of this method is that it provides a computational framework for the Griffith's energy balance. As you know, Griffith, one of the fathers of fracture mechanics, postulated that a crack will grow if the energy released by the solid reaches a critical value, the so-called critical energy release rate, or basically the material toughness. One can formulate the Griffith's energy balance in a variational form. However, minimization of this Griffith energy functional is hindered by the fact that the crack surface gamma is unknown. And here is where the phase field paradigm comes to our rescue by transforming the surface integral into a volume integral. Two things that I want to emphasize here. First, by looking at the first integral, you can see how the phase field parameter affects the stiffness of the solid through a degradation function, and therefore acting similar to continuum damage models. And from the second integral, you can see that there is a gradient term and consequently a length scale. So the model is non-local, which ensures mesh objectivity. So basically, results are mesh insensitive as long as this length scale parameter is resolved. You can get a good overview by looking at these two balance equations. The first equation is the solution to the deformation problem. Basically, the standard balance of linear momentum with the phase field degrading the stiffness of the solid. And the second equation is the phase field evolution, which is basically a competition between the strain energy density stored in the solid and the toughness of the material. And just by solving this simple system of equations, we can capture on the original finite element mesh in both 2D and 3D very complex cracking patterns like the one I'm showing on the screen. This is a crack branching due to the application of a dynamic load. So we can capture both branching and merging of cracks, nucleation from arbitrary sites, and complex crack trajectories without any convergence issues and no needs for remeshing. The next step is to include the effects of hydrogen. It's a very challenging problem that crosses the disciplines of material science, structural mechanics, and chemistry. But in broad terms, what we know is that atoms of hydrogen enter the material, migrate fast through the crystal lattice, and are attracted to areas of high hydrostatic stress or high volumetric strains, where the lattice expands and there are more space for hydrogen to accumulate. So first of all, we model hydrogen transport based on an extension of Fick's law of mass diffusion, basically the third equation, in which hydrogen diffusion is partially driven by the gradients of hydrostatic stress. In addition, we made the toughness of the material depend on the hydrogen concentration, as we see in experiments. The question is, of course, how to define that dependency. The logic that we follow is an atomistically inspired degradation law. So based on atomistic simulations, what we see is that the fracture surface energy decreases with the hydrogen occupancy. So quantitatively, by running atomistic or DFT calculations, we can see how much the fracture energy decreases with the hydrogen content. So for example, if your interface is full of hydrogen, which corresponds to an occupancy of 1, you reduce your fracture energy by 40%. And that explains why hydrogen is so dangerous for metallic materials. And finally, we incorporate the effect of fatigue damage into the modeling framework. And this is done by introducing a fatigue degradation function, which effectively modulates the fracture toughness of the material as a function of the fatigue history experienced by the solid. And the fatigue history variable, alpha bar, is chosen as a cumulation of elastic strain energy stored in the solid, which is also degraded by the phase field damage variable. Note that the accumulation of this fatigue history variable only takes place during the loading stage and not unloading. And for values below the fatigue threshold controlling parameter, alpha t, the fracture energy remains unaffected by fatigue. Okay, now I'm going to show you some results of this study. But first, let me mention that the modeling framework here is implemented in the commercial finite element package Abacus using its user-defined subroutines. And the coupled finite element equations are solved in an implicit time integration scheme using a residual control-based staggered algorithm. We have addressed several case studies to investigate the performance of our numerical implementation. The first case study is a well-known boundary layer formulation, which is used to gain insight into fatigue crack growth under small-scale yielding conditions. So what we have in the left figure is the crack extension as a function of the number of cycles and for different environments. The results shown here reveal that the model is able to capture the expected trends. For a given number of cycles, the higher the hydrogen concentration, the larger the crack extension. In addition, as you can see in the left figure, the model is capable of naturally providing as an output the Paris law behavior and the role of hydrogen on it. So what we have here is the fatigue crack growth rates, or basically the speed of the fatigue crack growth as a function of the normalized stress intensity factor. So for a given stress intensity factor, faster fatigue crack growth are observed as the hydrogen content is increased. In addition, as you can see in the right figure, the model also captures another widely observed experimental trend. So what we have here is the speed of the fatigue crack growth as a function of the normalized frequency. In general, the fatigue behavior of metals in the presence of hydrogen varies between two limiting cases, as I'm showing in this figure. First, we have fastest or high loading frequency, where hydrogen does not have enough time to diffuse to the fracture process zone, and therefore the susceptibility to embrittlement reduces. On the other hand, we have slow test or low frequency, where hydrogen atoms have sufficient time to accumulate in areas of high hydrostatic stress and therefore magnifying the embrittlement. And you can see how the model easily captures the smooth transition between these two limiting cases. So the next case study is a notched cylindrical bar, which is subject to uniaxial tension cyclic loading and exposed to different environments. As you can see in the left figure, virtual ascent curves are obtained for this specific case study. So what we have here is the number of cycles to failure in the horizontal axis and the normalized stress amplitude in the vertical axis. So as you can see, for a given stress amplitude, shorter fatigue lives are observed as the hydrogen content is increased. And in all cases, the number of cycles to failure increases with decreasing stress amplitude, which is basically expected for a typical ascent curve. And here, the slope of the ascent curves appear to be rather insensitive to the hydrogen content. And on the right side, I'm showing two contour plots. The one at the top is the evolution of the phase field parameter. The blue color corresponds to undamaged material points, while the red color corresponds to a crack. So basically, you can see how the model captures fatigue crack nucleation and propagation from a notch and in the absence of a stress singularity. And the other contour plot at the bottom is the hydrogen distribution, which is normalized by the hydrogen concentration of the environment. For example, this could be a part of an offshore monopile for a wind turbine, which is exposed to seawater. And you can see how the environment immediately occupies the space created with crack advance. And in conclusion, we compare our model predictions with ascent curves obtained from fatigue experiments on smooth samples. So basically, a typical dog bone specimen, which is widely used in fatigue experiments. The samples here are subject to uniaxial tension compression cyclic loading and tested in both air and high pressure hydrogen gas. And this is done for two types of steel. So what we can see here is that despite the scatter, which is typically associated with these fatigue experiments, the virtual ascent curves predicted here are in a good agreement with the measured data. Okay, and at the end, let me conclude my presentation here. We have presented a phase field formulation for hydrogen-assisted fatigue. We have shown that the model is able to predict fatigue crack nucleation and growth for arbitrary loading patterns, geometries, and environments. Paris law behavior and the role of hydrogen on it is naturally recovered by the model. And then the influence of the loading frequency is quantified, and the resulting regimes are also mapped. And finally, virtual ascent curves are obtained, showing a good agreement with experiments. Thank you very much for listening, and also many thanks to my academic and industrial partners. Thank you.